Commission, also the Vikram Sarabhai Professor at the ISRO, with lifelong contributions to space science. And he's also on the governing council of the Indian Institute of Science, steered and implemented several application oriented Indian space program in aspects of Earth observation, communication, navigation, meteorology, and space science. And he also, with regard to especially the indigenous launch vehicles, Professor Kiran Kumar has led and designed over 50 different electro-optical imaging sensors that were flown on several space-borne platforms, including the Bhaskara in 1979. His role in Chandrayaan-1, the mission, and the Mars orbiter mission are well known. Dr. Kiran Kumar has been the chair of the Committee of Earth Observation Satellites, coordination group of the meteorological satellites, expert team under World Organization, and also with regard to the Indo-US joint cooperation on the space program with regard to civilian users. With over 85 publications, Dr. Kiran Kumar has been honored by 18 Indian institutions with honorary doctorate. Dr. Kiran Kumar is the president of the Aeronautical Society of India, fellow of the Indian National Academy of Engineering, National Academy of Sciences India, Indian Society of Remote Sensing, and several other academies. Also, importantly, International Academy of Astronauts, and his contributions have brought him the Karnataka Rajyotsava Award as well as the National Civilian Honor Padma Shri. The Indian Institute of Science, the Gujarat Ratna, G.M. Modi Science Award, and also is recipient of the International Cabin Wings Award of the Aerospace Astronautical Society, and the Graduate Aerospace Laboratory of the California Institute of Technology, United States. The highest civilian honor by the government of France has also been conferred on Dr. A.S. Kiran Kumar. With these, I would like to mention we are proud that he is the recipient of the Karnataka Science Technology Academy Lifetime Achievement Award. At this occasion, we have been joined by 7 colleagues, another awardee, Dr. B.S. Shankar, the members of the KSTA, Dr. H. Rajasab, Dr. E. Eknath, Dr. D. Chandegowda, among others, and also Dr. Abhishek, and my colleagues here in the academy, also we have Dr. H.S. Savitri, another member of the KSTA, we have Dr. A.M. Ramesh, the CEO of the academy, Mr. Anand, Dr. Anand, and Mr. Umesh, several others, and a large number of audience who have joined on this web talk, apart from the YouTube viewers. So on this occasion of the Bharat Swatantra Amrit Mahotsava special talk series, on behalf of all of us, we feel privileged to welcome the speaker for today's session, Dr. Padma Shri, Dr. A.S. Kiran Kumar, and request you, sir, to speak on the topic that you have chosen, Indian Space Program, Contributions to Independent India. We are honored that you are with us, and now we request Dr. Kiran Kumar for the talk. Thank you, sir.
Yes, sir. Slides are visible, sir, now. Sir, please unmute, sir. Sir, we cannot hear you, sir. Please unmute, sir. Yes, sir.
Thank you very much, Dr. Ivan, for this opportunity to be part of the 75th anniversary of Indian independence. And on this occasion, KSTA is organizing a series of talks from people and then bringing to Karnataka people and all others who are joining an opportunity to listen to the various developments that have happened. And at the outset, I compliment KSTA for organizing this and giving me an opportunity to speak to the audience on India's space program and its contribution to independent India. Probably we are all quite familiar that space program would not have been possible but for the gentleman whom you are seeing on the screen, Dr. Vikram Sarabhai. And what he said initially at the beginning makes a huge sense. See, he said our national goals involve leapfrogging from a state of economic backwardness and social disabilities, attempting to achieve in a few decades a change which has historically taken centuries in other lands. This involves innovation at all levels. And he also went on to say that a positive approach out of our predicament lies in finding solutions where the particular disadvantage of developing nations, which is that they have little to build on, is made an asset rather than a liability. It is necessary for them to develop competence in advanced technologies and deploy them for solution of particular problems, not for prestige, but based on sound technical and economic evaluation involving commitment of real resources. It was Dr. Vikram Sarabhai who was responsible for bringing in the applications of space technology for development in India. What he started for use of space technology for national development has gone on with capability demonstration, capacity buildup for harnessing space technology, basically to meet national, societal, and strategic needs. And also now the emphasis is moving to being a significant player in space economy. Now, just I would like to trace how India developed its space program and in the process bring to you how the space technology has contributed to the growth of independent India. See, way back in 60s, the setting up of Tumba Equatorial Rocket Launching Site was one of the activities where Dr. Sarabhai, with the help of his friends from various countries like USSR, USA, France, Germany, etc., brought in sounding rockets in the form of okay. Then apart from this, there was also activities that were going on for making sure remote sensing experiments, whether it is a coconut root wilt disease or conducting some balloon experiments or helicopter and aircraft experiments, were all initiated at the beginning. And one of the key things what Dr. Sarabhai did during the initial days was to conduct a socio-technological experiment, largest of its kind in the world, a unique experiment where he convinced the Americans that they should allow us to borrow one of their most advanced technology satellite called ATS-F at that time. And that satellite, which is a geostationary satellite, was moved over to the Indian longitude, and in about 2,400 remote villages covering almost about 2 lakh people and remote places of the country, training about 50,000 primary school science teachers in 1 year and also bringing to the farmers information about farming practices and then welfare and health information to the villagers. This was done using what we are familiar today with direct to home television. Equivalent of that was done way back in 75 by building the technology. And it was this experiment which convinced the government of India that space technology is the route to go for bringing in specific information to the entire community, entire citizens of the country. Because you're all quite familiar, India being a vast country with many unreachable places, very widely varying terrains, it would have been extremely difficult if you were to follow the technology available at that point of time of building terrestrial transmission towers, linking them with microwave towers every 1 kilometer. Not only it would have taken a long time to establish that, but also it would have costed much more. So it was this foresight and visionary approach of Dr. Sarabhai, which actually he initiated, but unfortunately he himself did not live beyond 71. And the activities what he had initiated was carried out subsequently by people like Dr. Satish Dhawan, Professor U.R. Rao, then Dr. Kasturi Rangan, and Madhavan Nair, Radhakrishnan, and others. And using this satellite instructional television experiment, which was the world's largest experiment conducted at that time, demonstrated to the country that space technology is the way to go for communication and broadcasting. And what India did at that time was making use of the space technology. It was broadcasting, communication, and meteorology. These three functionalities were built into a single satellite system, INSAT-1. And this had to be done, though nobody had realized at that point a satellite of that complexity. We had to do that because we could not afford 3 independent launches and 3 independent satellites for such an activity. And it was a very complex system, and this was conceived by ISRO designers, and it was built. The first generation satellites were built by an American firm, but then beyond that, all the subsequent communication satellites, whether it's INSAT-2, INSAT-3, the 4 series or the GSAT series, they have all been realized indigenously. And today we have a technological capability of building communication satellite. We already have a number of satellites in operation, which gives us capability to provide direct to home television, VSAT connectivity, or telemedicine, teleeducation. A host of such capabilities have all been established during this period. And just to bring a perspective, probably some of you who are familiar in the 70s and 80s, if you were to contact anybody who is a friend or a relative who is some distance away from you, you had to adopt a person-to-person call and then wait for hours at Central Telegraph Office to reach out to the person. But today, by virtue of space technology based satellites, geostationary satellites, and low Earth orbiting satellites, a small gadget handheld can talk to anybody across the globe. So all this is possible because of the visionary approach of Dr. Sarabhai and the communications technology built in the country. And today, country is benefiting from these communication capabilities. And another thing that's happening is also what is called as high throughput satellite, where India is trying to provide to the Gram Panchayats high bandwidth or broadband connectivity so that the governance activities at the Gram Panchayats can happen and digital India activities can be provided very effective support. Connecting more than 6,500 Gram Panchayats is a part of this program, and already GSAT 11 is there, 19 is there, and very soon 2024 and other satellites are going to provide these capabilities of going beyond 100 Gbps. So this is one which enable communication to effectively reach out to the entire country. Then another very important development that was required was inputs for weather forecasting. Probably all of you are quite familiar that in the earlier decades, when we had super cyclones hitting the coast, India has a long coastline of 7,500 kilometers. And in any of these coastal regions, if a super cyclone hits, we used to have loss of life in the range of 10,000 to 20,000 people. And towards this also, the space technology provides a very good capability of having geostationary satellites providing continuous observation of cloud cover, temperature and humidity profiles. And based on this, which goes into the numerical weather forecasting models of the country, and using them, today we have a capability where every 15 minutes you can observe India and its surroundings, and that in turn enables the country to see, for example, what's happening with the clouds, cloud motion vectors, and temperature and humidity profiles. And today, both INSAT 3D and 3DR are capable of providing temperature and humidity profiles in vertical direction, and all this data goes into the numerical weather forecasting model. And with that, the India Meteorology Department is able to provide early warning to the disaster relief agency. And by evacuating the people from the coastline, we are able to actually save lives during the super cyclone periods. Another very important development that happened is when Dr. Sarabhai initially brought in the use of sounding technology rockets. It was assembled in the church building, what you are seeing in this slide. He could bring that sounding rockets in the form of kits by convincing his scientific friends across the globe that if we conduct upper atmospheric research at Tumba, it would benefit the global scientific community. But then to perform this experiment at Tumba, he had to actually convince the fishermen in the beach there. And for this, he had to actually take the help of the priest of this church, who could also help in convincing the fishermen. And what the fishermen were told is, if you vacate this place and provide opportunity for these experiments to be conducted, then at some point in future, the country will benefit. But as though to prove this point and as though to demonstrate this, what ISRO was able to do is actually by building a satellite called OceanSat, where the satellite looks at the Earth, the oceans, by looking at the color of the ocean and then the thermal, you are able to actually determine the prospective fishing zone or identifying the chlorophyll, and through the chlorophyll, the food chain of the fish, and then determine where in the ocean one can get fish catch. And this by 1999, through the pager system and electronic board systems, and this manner through the fisher communities association, fishermen were being provided information. But with the recent launch of our NAVIC, today we have a capability where a fisherman holding a small mobile, a handheld device, though the mobile itself does not have any connectivity to the terrestrial tower, you can easily imagine when the fisherman gets into the ocean, few kilometers away from the coast, no terrestrial link is possible for him. But then with the help of the NAVIC satellite and an app on the mobile, he gets information in such a way that a video compass directs him to the prospective fishing zone, that is where to catch the fish. And then in his mother tongue, through the app, he gets specific information on the whether it's the weather, sea state roughness, or even if he's approaching the international boundaries, any of these, he gets an alert in his mother tongue. So here you can see that the use of most advanced technology of building satellites and payloads, building launch vehicles, and then launching them into orbit, and through that providing a person who does not know reading or writing to carry out his livelihood supporting activity. So it is one of the very unique capabilities which space technology has provided to the country today. And then apart from communication and meteorology satellites, India also developed the two programs. One is called Gagan. Gagan is what is a GPS aided geo-augmented navigation system. What this does is when an aircraft flies over across the globe, the Indian subcontinent, there was a void. The use of GPS satellites and a specific augmented receiver on this aircraft helps the aircraft its position very accurately with safety of life and integrity of service guaranteed. So India started providing Gagan capability by flying these payloads, Gagan payloads, on 3 of its satellites and working with Airports Authority of India and certifying the use of these signals over the Indian subcontinent. Today, aircrafts are making use of it not only for their en route planning, but also for precision landing, and the further activities are developing on this. And this is one of the capabilities which India is having and is also providing to Indian subcontinent. Other than this, in NAVIC, again, a very unique solution has been adopted, where unlike global positioning systems, which the countries like USA, USSR, or China and Europe are adopting, GPS, GLONASS, BEIDO, or Galileo, requires between 24 to 32 satellite constellation operating in mid-orbit of up to 20,000 kilometers. But then what India adopted is a unique concept of making use of only 7 geostationary and geosynchronous satellites, and using this providing beyond Indian boundaries up to 1500 kilometers a capability of determining your own latitude, longitude, and height information, which is being today used for a large number of applications, whether it is for vehicle tracking and fleet management, maritime service, railway activities, railway operations, or even providing for unmanned railway crossings. So all of this, a unique 7 satellite constellation of NAVIC is providing its inputs. So here again, Sagar Mitra, based on the NAVIC and other communication and remote sensing satellite, a host of capabilities, including a distress alert terminal and then mobile terminals, are all provided today to the user community. Then this slide also showcases to you some of the activities which the railways are doing using both the navigation as well as communication capabilities that exist. One, the continuous linkage of trains moving on the rail are connected, and the level crossing and unmanned level crossing, there are provisions made, and progressively more and more trains are being fitted with these gadgets, and the railway service is actually providing improved capabilities with these facilities. Then for disaster management, again, a host of developments have happened, like I mentioned, whether it is a weather forecasting related or forest fire, floods, then drought monitoring. And we also provide to international agencies data collected from our remote sensing satellites. For providing all this, India has been making use of its technological capabilities. What it started was way back in 70s, in 75, the first satellite was launched, Aryabhata, when Russians offered to provide launch facility for an Indian satellite, and using that Aryabhata was launched. But then developing Bhaskara 1 and 2, which were remote sensing satellites done using, again, the facility offered by Russians to support 2 of our satellite launches. Then starting from that time, progressively been building capability to look at Earth from space. As you can easily imagine, when you're orbiting the Earth, you can see different portions of the globe and you can cover practically the entire globe. And today we have built, with increasing complexity, satellites capable of taking multispectral imagery. To start with, it was IRS-1 series, which had about 70-meter and 35-meter resolution, 4 spectral bands. Progressively, we have increased it, and today we have spatial resolution of submeters, almost 30 centimeters, and then multispectral capability. And not only from low Earth orbiting platforms, but also from geostationary platforms, where you can look at Earth almost continuously, and every few seconds, a few minutes, you can cover portions of the Indian subcontinent and provide inputs. Few things that happened during the course of these realizations was India actually developed some unique capabilities. One of them was to meet the specific requirements of our agricultural monitoring. We came up with a 3-tier imaging system, which provides in a common platform, very coarse resolution, high temporal revisit, then medium resolution and high resolution multispectral data, which is being used for various applications. Today, we have also developed airborne and spaceborne hyperspectral imaging, which enables a host of applications, including crop, the pest monitoring, and also even for many strategic uses applications. Probably many of you will be wondering, during the months of monsoon, June to September, if you take, when you look from space, the Indian subcontinent will be covered with clouds. So how can you see using visible or near infrared data? But then there are special sensors called microwave sensors, which are operating in different electromagnetic radiation. And this provides a unique capability of being able to see through the clouds, like what we can see through the glass in a transparent manner. We can see the object and various aspects of Earth by making use of microwave sensors. So we have developed a number of microwave sensors, starting from Samir in 79, which was a radiometer. Today, we have got synthetic aperture radars and a scatterometer. Now, scatterometer is again a very unique instrument, which helps looking at the ocean wind vectors, which forms a very important component in the numerical weather forecasting model globally. And India has been providing this input to the global weather forecasting community, and this has been a very useful contribution to the global activities of weather monitoring and weather forecasting. Then you have a synthetic aperture radar, altimeter, etc. Then in meteorological satellite, starting with OceanSat, means OceanSat 1 for ocean color observation, and also using the ocean, apart from ocean color, you have got thermal fronts, and then you can make use of it for algal plumes and many other activities, including the planning for the ship routes, etc. And building Saral and Altica. Saral also had a microwave humidity sounder, and then megatropics, then SCATSAT, all these instruments, and then in the optical going up to inside 3DR. We also built a three-dimensional digital elevation model generating capability by having along track stereo viewing. And this satellite was launched in 2005, and it provided for the not only the entire country, but also all the neighboring regions and other regions of interest to India. And today we have got the digital elevation model, which forms as the backdrop for a large number of remote sensing applications. And just generating capability and generating data and information alone is not adequate. So what ISRO was doing was working with various institutions, both central and state governments, and then try to make them use the knowledge and the data acquired through the space technology. And towards this, Forest Survey of India started using the satellite-based remote sensing data and generate biennial state of forest report. This started way back in '87. Then INCOIS, that Indian National Ocean Information System, under that potential fishing zone advisory, and progressively increasing to NAVIC and today's system. Then Ministry of Agriculture started using it by establishing Mahalanobis Crop Forecasting Center in 2012. So you can see some departments started using early, some departments took more time. And then Ministry of Water Resources, Sedimentary Survey, Irrigation and Infrastructure Monitoring, then Airports Authority of India making use of civil aviation and GPS aided geo augmented navigation system. So in this manner, the various entities and central and state government started adopting use of space technology for various activities. But then the demand and requirement was much more. And today, what we have, space technology inputs are optical microwave sensors providing multispectral and hyperspectral data. Then digital elevation model, which forms the backdrop. Then in situ observation sensors and data collection platforms provided via the communication links from satellites. Then navigation enabled position information, and then using mobiles and crowdsourcing techniques, a lot of in situ information. All of that comes into the modeling technologies and a suite of applications which have been developed, which helps socio-economic security, sustainable development, disaster risk reduction, and governance. And all this started happening with a greater vigor and push when Honorable Prime Minister of the country started pushing the various stakeholders to make use of space technology based inputs in their activity. In fact, when this program was conducted in 2015 in Delhi, more than 1,000 secretaries of state and central government departments were brought together, and it was showcased how space technology can provide specific inputs and benefit the various activities that are going on. And in this program, Honorable Prime Minister himself spoke extempore for about 45 minutes and telling the secretaries how space technology based inputs can be used for monitoring, planning, and various other activities, because he, the Prime Minister, when he was the Chief Minister of Gujarat, had made use of this extensively by working with BISAC, an institution which worked with SAC to provide various capabilities. And with this push coming from the people who are governing the country, these things started accelerating and moving at a much faster pace. Then a large number of activities was taken up, more than 158 projects, and then space technology cells were getting established in various departments. Then farmer-centric initiatives for food security mission, Blue Revolution, then urban development and Amrit. So like this, in some of the subsequent slides, I'll show this. So the significant push came during that time. Then with this, today what is being done is a periodic assessment of natural resources, land use, land cover maps at 250,000 scale. Already 16 cycles of data have been generated and these atlases are available. Then forest cover maps at 1:50,000 scale, biennial by the Forest Department, Forest Survey of India. Then land use, land cover in both 50,000 and 10,000 scale. Then similarly wasteland mapping, then geomorphology, desertification. So all these are going in as database. Then geospatial support for governance, integrated watershed management project, or the Amrit cities where base maps are being generated for 239 Amrit cities using the urban and regional development plans and capacity building in the various institutions and local bodies, and then Manrega and also PM Awas Yojana. In all these, geospatial technology is getting used. Now, space technology utilization in food security and agricultural assessment, actually crop production forecasting and assessment, agromet product, inputs for agriculture, space-based solution for crop insurance, decision support system are all happening using these data sets. Then space application, apart from this in agriculture, you also have horticulture, then crop insurance, sericulture, and a host of other things are done. Crop insurance, coming to that, providing crop mapping and aerial discrepancy analysis, prevented failed sowing information, and then remote sensing based indices, geotagged locations, and then smart sampling and optimization of crop cutting experiment. A host of this is being done on a regular basis. Now, geospatial component for National Hydrology Project is also another thing where the flood forecast and inundations using microwave data and also airborne sensor. Then daily and near real time snow melt rate information using the Indian Himalayan River Basin studies, then training programs and glacial studies are all part of the work that is progressing significantly. Then Jal Shakti Abhiyan is what the central government is now doing, where it's trying to bring in water resource as a single entity and trying to bring together the various department work, and ISRO is also contributing to the various activities of this by not only conducting technical workshop, but also by providing various inputs, and through Bhuvan Jal Shakti Abhiyan portal is also established. Then similarly, whether it is for identifying mining areas and ores for the Manganese Ore India Limited, or for disaster management support, whether flood, cyclone, forest fire, early warning system, hazard zonation, or in all these areas, data from both microwave and high resolution optical satellites come. Recently, including for locust surveillance using space-based inputs, work and modeling is being done. Then this is another very important aspect where the governance which can happen at the panchayat level can to the panchayats, the sarpanch and the elected representatives of the panchayats, specific information about their own village, surrounding villages, and what is happening around them, and enabling them to actually carry out planning activity. Towards this, efforts to actually engage the academic institutions and student community is constantly being attempted. And even in Karnataka, use in Mangalore, some other district, the academic institution with a number of teachers and students provided using in situ survey and based on space input provided to the collector a host of information. And this is another area where geospatial modeling for Gram Panchayat development plans, etc. And in addition to Manrega inputs is happening. Water pollution monitoring, again based on space-based inputs. These are all actually continuously improving activities with more and more improved models being able to provide inputs, whether it's air pollution or providing inputs is also happening. So all this data is also being provided using various geospatial portals, both Department of Space and other departments. And this gives a glimpse of many of those portals which have been developed. While all this was going on, India also made sure that it is able to provide to its scientific and research community a capability to make use of the space technology to look beyond Earth itself and then get into space and study from low Earth orbit to geo platforms to Moon, Mars, and planetary studies. And for this, various different kinds of orbits need to be used, from the equatorial to inclined to polar orbits. And we also made use of some unique combination of orbits for reaching to Moon and Mars. And we'll see some details subsequently. And today, by providing programs through Chandrayaan-1, Chandrayaan-2, Mars, and Astrosat missions, we have been able to provide a significant input to the scientific and technical academic community. Chandrayaan-1, probably you're familiar that it carried about 11 instruments, and some of them came from our international partners. But then the unique thing about this was the satellite gets a credit for discovering presence of water molecules on Moon. And then Chandrayaan-2, also we have a number of specific instruments, which is an improvement over what was done in Chandrayaan-1. This is a dual frequency SAR, which can look at permanently shadowed regions on the Moon. And then the Mars orbiter mission, which was done in a very unique way by making use of our PSLV and reaching in the very first attempt. And while the initial plan was the satellite will operate for about 6 months, see, today we have already completed 6 years, and very soon it will complete 7 years, and it is providing a unique set of data. Chandrayaan-2 also carries, though Chandrayaan-2 itself, we had difficulties in succeeding effective landing on the soft landing on the Moon. Today, Chandrayaan-2 is providing a unique set of data with very much improved resolution and spectral and microwave sensing, X-ray monitoring, and a host of such instruments. And it is actually improving on the scientific knowledge which is gained from such platforms. This is an example of how a microwave sensor can look at permanently shadowed regions and create three-dimensional information about this. And this microwave sensor also provides inputs for identifying presence of water ice, etc. Work is in progress using that. Another very important development that happened was India was able to launch a multi-wavelength space observatory, a first dedicated astronomy satellite. The uniqueness of this is ISRO enabled these institutions like Indian Institute of Astrophysics, Bangalore, Inter-University Center for Astronomy and Astrophysics, Pune, then Tata Institute of Fundamental Research, Raman Research Institute, then IUCAS, as I mentioned. All these institutions were enabled to develop instruments, and these instruments were flown on the satellite. And this satellite is already done some wonderful things because the satellite carries a very unique the the far ultraviolet telescope, which has the highest angular resolution in the world. And by looking at a specific region identified by Hubble, this was able to look at some very new information. And that information was actually coming from a galaxy called AUD FS101, 9.3 billion light years away from us. And this is the first time anybody was able to pick up signals in this particular wavelength region. And it gives clue to how dark ages of the universe ended, and it's already making a huge impact. And ISRO is also enabling a number of other capacity building activities. Today, we have the country's only 180 nanometer fabrication facility, which is run at Chandigarh and which has got a capability of doing various components and chips. So we have already used and flown on our launch vehicles and satellites a number of electronic components built using this capability. Similarly, using a Vikram processor and also Sigma Delta ADC. And for doing all this activity, a large number of developing aerodynamic simulators or the facilities have also been done. A supercomputer facility was established and it provided input for various modeling activities. Now, for doing all this, obviously, one needed to develop launch vehicle technology, which starting from sounding rockets, let's show that. Okay, starting from sounding rockets way back in 63, which were assembled in the form of kits, progressively increased capacity of 40 kg using SLV up to 150 kg in ASLV, and then PSLV, GSLV, and then GSLV Mark III were done. Now, PSLV itself, if you take, we have used it for very unique demonstration. In 2007, we had the, or even before that, 2002, we used the PSL putting a satellite stationary transfer orbit. In fact, this was the first time anybody could put a geostationary transfer orbit satellite without a cryogenic engine. And then progressively satellite recovery experiment, Chandrayaan, then making use of Mars orbit, PSLV for Mars orbiter mission, and also launching 104 satellites in a single launch, which became a unique feature and unique feat in the world. And all these capabilities were indigenously realized. Similarly, the capability of geostationary satellite launch vehicle started with the expectation of cryo engines technology being taken from Russia. But then how things played out geopolitically, we had to depend on our own the cryogenic engine development, and beyond 2014, we have been able to make use of our own cryogenic engine and launch geostationary satellite and geostationary platforms being done. Then Mark III, which is giving us up to 4 tons, and this satellite, this launch vehicle is also the one which is we're going to work for putting astronauts into space. And a huge number of activities had to be done and large facilities had to be established for achieving this. Today, you'll be happy to know that more than 3 versions of cryogenic engines have been successfully developed, and then further versions of semi-cryo engine development is in progress. And not only development of these technology, but also scramjet engine, and then using this for re-entry mission, crew module re-entry, or winged re-entry vehicle. All these R&D activities are also a necessary thing, and these technologies are progressively being built. You can see that you need to conduct all these R&D activities, and this is being progressively done using the capabilities that have been established. Then currently the ISRO is also working on putting Gagannauts or Vyomanauts into orbit and bring them back safely. Originally, the plan was to do it before the 75th anniversary of Indian independence, but then because of COVID and various other issues, this is going to take a little longer time. But then all the technology developments and then ensuring that human rating of the launch vehicle. Probably you will listen a lot more on this by Dr. Suresh when he is presenting and his talk. And the Gaganyaan program itself, India is trying to link a huge amount of academia industry interface and then bringing in synergy with the science and technology activities across the country for in a large number of areas. Apart from all this, what ISRO was also doing is work on an international cooperative missions. I mentioned about Megatropics, and Megatropics actually provided the temperature and humidity profiles in microwave region. And this also provides specific inputs to the numerical weather forecasting models. And Saral Arctica is an Indo-French mission to study sea surface altitudes. And then these data are shared with EUMETSAT, NASA, and many other space agencies. Then India, true to its heritage, also the concept of sharing the knowledge and the knowledge and skills you acquire should also be benefiting not only yourself, but others. In this mode, India will use space technological capability to provide to the SAARC countries of Bangladesh, Bhutan, Maldives, Nepal, and Sri Lanka. The satellite-based communication transponder service has been provided, and also these is being used for various activities in these countries and using space technology capability for supporting the neighboring countries also. Today, India is working with NASA on a system called NASA ISRO Synthetic Aperture Radar Mission. It's one of the most advanced technology satellites, which costs more than $1 billion, out of which America is spending or NASA is spending about $0.9 billion and India is spending about 0.1. And here again, what is important to realize is people or the countries, others recognize you only when you are capable of doing something. Though there was a large interaction right from early days with NASA, NASA was ready to carry out a common mission only when ISRO demonstrated its Chandrayaan program and then Mars mission and also its own synthetic aperture radar. Then we started working together for this common mission, and then the capability established is getting effective usage for research community. Then today you have a large number of inputs which are going for both climate studies and environment studies, whether it is for terrestrial, ocean information, atmospheric information, cryospheric, or model-derived information. All that is also available on NICES, that is National Information System for Climate and Environment Studies. Then even during COVID, a host of activities were done where the state and central governments were provided with specific inputs, helping them in tracking, hotspot identification, and doing certain activities for vegetable markets, food for the needy, providing that, home isolation, pollution studies, and a host of such activities. So is what India has done right from the beginning is what is called as leapfrogging approach. That is, you try to make use of a innovatively accessible technology, and then what is not accessible, you build your own. And all of this you do for addressing specific societal problems, whether it was communication and broadcasting, or navigation, or remote sensing, or space missions going beyond the planet Earth, or even providing unique capabilities to the scientific community, research community in the country. And like whether putting some 104 satellites in a single launch. In all this, what you can see is a approach of making use of accessible technology, building indigenously new technological capabilities, and using them, all of them, to address specific problems you have. And for that, even if you require to develop some new methods of doing, go ahead and do it. For example, we showcase how fisheries got the problem of fisheries was addressed. Similarly, how the problem of communication, meteorology, and broadcasting was done using a unique 3-in-1 satellite, the like of which did not exist at the point of realization. And then making use of all opportunities of international cooperation, whether when the Russians offered to launch satellites or Ariane offered to launch a payload satellite for us, Apple was used. And when we develop capabilities, we have also started providing inputs to the global community, whether it's for numerical weather forecasting or disaster charters, or even neighboring countries for communication and providing specific inputs. Now, while all this is happening, the capacity has been built up. Today, what ISRO is looking at is moving ahead, and the government of India is moving ahead, is actually trying to look at how this technological base of what a very few countries have achieved. Today, if you see, India is between 5th and 6th in various segments. And this unique capability of building launch vehicles, building satellites, building application capabilities using the satellite data, all these unique capabilities, how to leverage this and become a significant player in the global space economy. Now, space economy is moving towards almost $400 billion in the coming days and years. And towards this, if India has to take advantage, what is needed is the more and more participation of industry, academia, and startups and the student community. And towards this, central government is also changing its policies, enabling, supporting, and promoting the private enterprises to not only take advantage of the facilities that have been established, be a partner, or even be solution providers. Already, some companies have started looking at how to have their own communication satellites, get it built and launched, whether it is from within the country or even from outside. Then how the space technology developed is being effectively utilized. And towards this, things are moving, and more startups have started coming. Already there are companies which have started actually building on launch vehicles, satellites, and various application activities. So in a nutshell, if you were to say, use of space technology, which was a very new capability which came up when Russians first put a satellite into orbit way back in 57. We had the visionary scientist like Dr. Sarabhai, who could foresee that unless India starts working in this area of space technology, our development and our ability to be a significant player in the global arena would be affected. And he pushed and started this, and over the last 5 to 6 decades, continuously the efforts have paved the way, and today India is on the threshold on the independent India, which is now looking to reach $5 trillion economy. And as its economy becomes stronger and stronger, now it is also trying to make its technological capability provide a become a significant player in the fourth frontier. The fourth frontier being after land, ocean, and air. Now space is the fourth frontier. You already have international entities like Elon Musk, Jeff Bezos, or other private companies entering and trying to capture the market of launch vehicles, satellites, even space tourism, space adventure, colonizing other planets in all these areas. So India is also trying to enable its commercial and private enterprise to move towards such activities so that India, by the 75th anniversary, it has achieved this, and in the coming years and decades, it is trying to become a forerunner or a leader among these areas. And towards this, work is in progress. And I would like to thank KSTA for giving me this opportunity to showcase to you the activities that have been done, how things have progressed. And of course, obviously, a period time like 45 to 50 minutes or 1 hour is hopefully inadequate to bring out every aspect of what has been done. But still, I'm sure you have got a glimpse of what has been achieved in this area. Thank you very much for the patient hearing, and I'm open for any discussions and question answers that you have, questions you have, which to the best of my ability I'll answer. Thank you very much.
Thank you, sir. Thank you very much for enlightening us on the entire space program and the contributions to the independent India. If we're able to talk like this, and the ISRO's contributions is so much, and your leadership had given a direction to the organization. We are grateful to you for this talk. And as you mentioned, at this time, if there are comments, questions to Professor Kiran Kumar, our audience, you are welcome, please. We have more than 260 colleagues in the audience, and then many more, as I said, YouTube viewers. Yeah, it's now time for discussion, please.
Thank you, sir. Now there is one question from Mukunda Nargunda. I would like to unmute them. They would like to ask a question to sir. Yes, Mukundji.
Sir, good morning, sir.
Yeah, good morning.
Kiran Kumar, sir, you are our inspiration, sir, for all the academic people also. Sir, I have one, and thank you very much for your informative and motivating presentation. Sir, I teach electronics to BSc students at Christ University, Bangalore, sir. I have one, I would like to know whether in our country, sir, do we have relevant electronics industries to support the ISRO's space programs? And also, kindly I request you to suggest how to enable our young students at our higher educational institutions like universities to get into space technology, especially electronics, sir.
Yeah, thank you for this question. See, today, for example, like I showed, the Semiconductors Limited has started making certain processes and certain electronic components, and actually the student community can use some of them in their projects and then build capabilities around that. That is one way where indigenous electronics based things. Of course, there's always an argument that these are 180 nanometer technologies, they're power hungry, etc., etc. But still, there are many activities which could be done even with this type of thing. And basically the idea of the student is to learn the process of doing things, learn the process of designing. Then when he has access to improved or better technologies, he can make use of it. So your question on the availability of electronic industry in the country, yes, there are many electronic industries which are actually developing some of the hardware required for supporting the communication as well as NAVIC application related activities. Things have started happening and there are a number of them. ISRO itself today is trying to provide many regional centers, and then it is also trying to provide incubation centers as well as facilities at these places where the academic institutions can work and then get access to some of the technology elements and work there. If you get in touch with our capacity building program office, you will be able to find much more information on this. So it's a continuous endeavor to enable academic institution by providing projects either through Respond or even directly during the course of project development. But with today's in-space and the new policies which the government is trying to bring, both academia as well as industry is likely to get involved in a much larger and faster manner than what had been happening in the past.
Thank you, sir. Sir, namaskar, sir.
Thank you.
Thank you very much, sir. Sir, any other questions from the participants? They can raise the hand. I can unmute them, or they can drop in the chat box. Meanwhile, over to you, Ramesh, sir. If any questions from the panelists, they can ask.
Thank you very much. Thanks for those comments and questions. Would like to once again, on behalf of all of us, thank Dr. Kiran Kumar Saab for this talk and inform our audience participants that next week on the 14th of July, Wednesday, same time, 11 o'clock, we have another space scientist coming in, Dr. B.N. Suresh, Chancellor of the Indian Institute of Space Research and a well-known space scientist. So we would request you to join us. And then the 28th, we have the talk by Professor Dr. Kasturi Rangan, and former Chairman ISRO. So this is the calendar for July 2021. We request you to join 2 more talks in the month of July, so 14th and 28th. With this, once again, thanking Dr. Kiran Kumar ji immensely, and request my colleague Dr. A. M. Ramesh, CEO of the Academy, for his words.
Good afternoon, sir. We have listened to a very scholastic and enlightening talk on Indian space program contribution to independent India by Padma Shri Dr. A.S. Kiran Kumar sir, former Chairman ISRO. Sir's talk gave a glimpse of space technology, including history of Indian space technology, how father of Indian space technology, Dr. Vikram Sarabhai, started space technology in India, then first space program of India site, PFZ, etc. And also, sir spoke about the future programs of ISRO and Indian endeavor to capture fourth frontier in the coming days. On behalf of KSTA and all of you present here, I am very thankful to Dr. Padma Shri Dr. S. Kiran Kumar sir for a very illuminating and distinguished talk. Thank you very much, sir. Thank you very much, sir.
Thank you very much.
I am very grateful to our Honorable Chairman, Professor S. Ayyappan, for initiating this very popular Bharat Swatantra Amrit Mahotsav series of distinguished talks. Thank you very much, sir. I would like to thank immensely our esteemed members of KSTA, Dr. H. Rajasab, Dr. A.E. Eknath, Dr. D. Chennegowda, Dr. H.S. Savitri, and also KSTA Lifetime Achievement Awardees, Dr. P.S. Shankar and Dr. Nagesh Hegde, for their presence in the webinar. We have with us senior scientists from space, Dr. V. Jayaraman, Dr. K. Ganesh Raj, Dr. Guru Prasad, in this talk. On behalf of all of you, I'm very thankful to these 3 space scientists for their presence in the webinar. I'm also thankful to senior academicians present here, Dr. K.V. Rao, Dr. Girija Shivkumar, Professor C.D. Patil, Dr. Chandan Keri, Dr. P.M. Patil, Dr. Vanitha Krishna, Dr. Y.C. Kamala, Dr. P.N. Kulkarni, Dr. Abhishek, Dr. Mahesh, Dr. Tabassum, Dr. Mukund, Dr. Suresh, Dr. Shubha, and many senior academicians who are present here. I'm also thankful to Garden City University, BTU, Surana College, and Gravity Science Foundation, and other institutes for supporting us in organizing this program. As our Honorable Chairman told, next Wednesday, that's 14 July, we have a distinguished talk by Padma Bhushan, Dr. B.N. Suresh, Chancellor IIST, on why is it rocket science. And also this week, tomorrow itself, we have a distinguished talk by Nimhan's expert, Dr. Falguni Anand. She will be delivering a talk on Parkinson's disease. I request all of you to kindly join these talks also. At this juncture, I would like to remember our former member of KST and renowned science communicator, Professor Aldoderi Sudhindra, for writing many articles on space technology in Canada and popularizing in the state. With this, I would like to thank everybody who are present here and also those who have joined this webinar on YouTube. Next, tomorrow, I request you to kindly join. Thank you very much. Thank you. Group Prasad sir, thank you.